Part 3 of the presentation will look at the second category of climate engineering methods, and I'm only going to mention 4 of them. The first is called stratospheric aerosol injection, and that involves bringing to high altitude aerosols. And there are several ways in which this could be done. The most cost-effective is probably by aeroplane. So you take the planes and they go up to high altitude, around 18 kilometers, which is some distance above commercial flights. They're limited to 11 or 12,000 meters, and the aerosols would be released. And what that accomplishes is an increase in the reflectivity or the albedo of the atmosphere. So some of the incoming solar radiation would be reflected back into space, and that will have a cooling effect. Now, this is a natural phenomenon. It occurs when you have volcanic eruptions. And the most dramatic example of that in the last century was Mount Pinatubo in the Philippines, which erupted in 1991, and it spewed out huge amounts of aerosols, including sulfur dioxide and dust, and which circulated around the atmosphere for about 3 years, and it reduced the global mean temperature by about 0.4 degrees centigrade, which is a huge effect Earth-wide from just one volcano. And in the northern hemisphere, the effect was slightly larger, 0.5 to 0.6 degrees centigrade. So what are the advantages and disadvantages of this technology? Well, one is that it's technically feasible. Clearly, it's possible to send up planes to high altitude and deliver the aerosols. Yes, it would be expensive, probably to the tune of billions of dollars, but a large country like the United States, or perhaps the European Union, or even large countries within Europe like Germany, they could do it. Now, the effects would be temporary, and that has an advantage and a disadvantage. The advantage is that if adverse effects occur, you can simply stop sending the planes up, and the aerosols are going to dissipate pretty quickly, a matter of, I would say weeks. But there's a disadvantage, and that is that you can't do this once and for all. You'd have to keep on delivering the aerosols up. So it's going to be an ongoing process, and the cost would mount over time. The second technique, called marine cloud brightening, is similar in terms of the physics. The goal here is to increase the albedo of clouds above the ocean, and that could be done by spraying seawater up to a certain altitude in the form of a spray. And that could be done by a large fleet of barges. The initial idea was to deploy maybe 1,500 barges, or unmanned ships, so you wouldn't have the labor cost involved, and they would spray the seawater into the clouds. And it's not so much the seawater which would be the benefit. Indeed, we know that water is a greenhouse gas, but it's the salt in the seawater, because the salt, being particulate, would form the nucleus of raindrops and so on. So that would increase the clouds, and the clouds being white have a greater reflectivity. So as far as the advantages and disadvantages of marine cloud brightening, they're similar to aerosol injection, but there are some differences. The first is that seawater, rather than aerosols, would be put into the atmosphere, and that has the advantage that seawater is well known. The possible drawbacks would be less than for the aerosols. The second is that the technology could perhaps be deployed regionally, so it wouldn't be worldwide. There'd be certain areas of the world where you want more cloud because of the cooling, and that could be the case with, let's say, southern Europe, where it's pretty warm, or it could be done in the Antarctic, right, to slow down the melting of the ice sheet, or indeed Greenland as well, because we know that if the Greenland ice sheet collapsed, that would contribute to a rather large increase in the sea level, and the same is true if parts of the Antarctic ice sheet dropped off. So there may be parts of the world where it's more important to maintain lower temperatures, and because the clouds don't move all that quickly, and they move in predictable directions usually, this technology could be regional. However, there would be spillover effects. If, say, a small country in Europe deployed the technology, almost inevitably there'd be effects on its neighbors, right? The clouds move from the host country to the other countries. The effects may be good, but there may be concerns in the countries where the effects are being felt. So some kind of international agreement, probably through existing international law, would be required. And indeed, that's true of the stratospheric aerosol injection as well. So it's unlikely that one country could go ahead on its own without getting buy-in from other countries. The third technology is the one which can be deployed at the smallest scale, and it's called passive daytime radiative cooling. Now I know that at night it tends to cool off, and that is because you don't have any more incoming energy from the sun, but the bodies which heat up during the day will re-radiate in the infrared part of the spectrum. So the goal here is to reduce the incoming radiation in the ultraviolet and the visible part of the spectrum, and then increase the re-radiation in the infrared. And that can be done using certain materials, which I show on the next slide. Now the schematic A at the bottom left shows the four movements of energy. The first is from the sun, that's directly from the sun. The second is from the atmosphere, if it's warmer than the surface. And then there can be energy moving in or out of the area under consideration through conduction or convection. And then you have the radiation, which is back into space. So the goal here is to reduce what's labeled there the P sun, the incoming radiation, and increase the P rad, the radiation in the infrared part of the spectrum out. And the ideal material is one which does that in the extreme. So we have on the right-hand side, panel B, an example where there's a certain amount of incoming radiation in the ultraviolet and the visible part of the spectrum. That's in yellow, and it tends to be greatest at the shortest wavelength. And then there's a region in the middle of the diagram where there's no radiation either inbound or outbound. And then in the infrared, you have what's shown in blue. So you want less yellow and more blue. And the ideal is to have some kind of a surface which takes in none of the incoming radiation. And that's shown, if you can see, by the red line running along the horizontal axis. And then you have a step function, and you have a maximum band in the spectrum for re-radiation. So that's the ideal. As far as I know, no materials will accomplish that, but the closer they can get to that, the better. And here's the second slide showing what kind of materials can be involved. They can be simply paints, basic product, plastics, polymer resins, and ceramics like tiles. And it can be applied to individual buildings, the walls and the windows, right? So a homeowner could do it, or an office building, or a garage, and so on. Right? So it might only cost a few $1,000s. So that's one of the advantages, implementable at low cost, and it's scalable because it can be simply applied to more and more buildings. Another advantage is that the effects are predictable, and indeed we experience that. If you're walking on black tarmac in the summer, it can be too hot in bare feet. Right? So it's black body and it absorbs a lot of radiation. If the pavement were repainted white, it's going to be a lot cooler, and that's good not only to touch, but it warms the nearby atmosphere less. And the same thing is true of clothing. In the summer, it's better to have white clothing. You don't get as hot if it's dark colors. There is a disadvantage, however, and that is that this technology doesn't work as well in humid climates and with cloud cover. And that tends to be the case in tropical climates, which is unfortunate because it's those climates which are most susceptible to climate change. It's already hot, and if it gets hotter yet, it may become uninhabitable, or you can no longer grow certain crops. So the economic activity can suffer, and also working outside, if it's 35 or 40 degrees centigrade or even warmer, can be very difficult, and there are hazards to the health. The final technology, which is the one furthest out, literally speaking, as well as figuratively, are what are called mirrors in space. And this refers to what you might expect. Mirrors deployed far out in space, which would reflect the sun's rays, so they never reach the Earth. And the idea goes back exactly a century. And then several decades later, in the 1980s, there was some research. And then there was a single test project done by the Russians in the 1990s. And there was a phase 1, a phase 2, 2.5, and it turned out to be unsuccessful. So it was abandoned, and there's been no further testing. There's been theorizing and so on and designing hypothetical mirrors, but not actually testing them at any scale. Even the smaller mirrors are going to be very large indeed, many square kilometers in area, and they're going to be fragile, pretty thin. So the question is, where's the material going to come to build them? And the answer is preferably from the moon, because with advances in technology and the knowledge now that the moon has water and so on, and you can undertake activities in shadowed areas which never receive the sun, it could be constructed out of materials there, and then the gravitational well of the moon is much smaller than for the Earth. So it would take less energy to hoist the components out into the locations where the mirrors are being deployed. And then the actual launch would probably not be done by rockets, but rather electromagnetic slingshots. And that technology exists. It would just have to be scaled up. And of course, a lot of energy would be required to boost objects into orbit, well, away from the moon. So what are the pluses and minuses of this technology? Well, it's a new one. It's just at the conceptual stage. Clearly, if you have a very large mirror, you can reflect an appreciable fraction of all the incoming solar radiation. And so it has the potential to materially combat climate change. But the disadvantages include the very high cost and the protracted time required to assemble the mirrors. It's somewhat doubtful that it could be done at scale before the end of this century. Second is the concern about damage. Now, the mirrors may be too far out to be affected by space debris from orbiting satellites, which are in near Earth orbit. But if it's a geostationary, or 36,000 kilometers, I think, out, or even further, where there are dangers of strikes by meteors, then repairs might be necessary. And that would be very difficult and costly. Probably, maybe robots could be deployed to do it, but maybe people would be required. And then if you have a huge mirror, which is darkening a part of the Earth and not affecting anything elsewhere, that could affect weather patterns. It's going to affect the temperature and hence the pressure differential in the atmosphere and alter not only the frequency of rain, but also the direction of the winds. Right, so it's high risk in that environmental sense. And then there's this brief blog by Yanakura at the RAND Corporation, sort of taking a balanced view that much needs to be learned, but this form of insurance is probably worth investing in case it needs to be deployed, so that if so, then it can be deployed more quickly than if you do nothing up to the point where you realize that it's going to be needed. Now here's the second slide on the mirrors in space showing the most ambitious proposal, 2,000 kilometer diameter mirror. And that's over 3 million square kilometers, so absolutely enormous, the size of a small country. And it would be built out of very thin glass, 10 micrometer. Right? So thin that you couldn't see it with the naked eye. Now the location matters because you want it to be fixed in place. You don't want it to drift out into space because then it's no longer going to be useful. So the most attractive location will be one of the so-called 5 Lagrange points. So these are points where a body, if located there, doesn't move relative to the Earth. It just stays at the same position. And there's a Lagrangian 2 point on the opposite side of the Sun, or away from the Earth, and then there's 3 others. But the Lagrangian 1 point is the logical choice because it will provide an umbrella-like effect on the Moon. And as the diagram shows, you have the Sun on the left, the Sun radiating in all directions, and the radiation to the right will be partially blocked by the mirror. Now things are not drawn to scale there. The mirror would be much smaller than the Earth, and it'd also be much closer than is shown. It'd be about 1.5 million kilometers away from the Earth, which is about 1% of the distance from the Earth to the Moon. So if you measure things in astronomical units, AU is indicated in the arrows at the bottom, 1/100th of an astronomical unit away from the Earth, and 99 hundredths of an astronomical unit away from the Sun. All right, so at least conceptually this technology is possible, but enormous investments would need to be made. So in a sense that might be the last ditch form of insurance which would be deployed if climate change simply goes out of control. So this table simply lists the technologies that we've looked at in this lecture. On the left we have the carbon dioxide removal technologies, and there are 8 there, and the solar radiation management 4. And I've put in bold or in color those technologies which are more far out, right, which have been thought about, but which are either turned out to be unsuccessful in these initially, such as seeding the oceans, or the direct air capture, which now appears to be going ahead in large scale, but so far very little capacity to draw out the carbon dioxide which is already in the air. And then with the solar radiation management, the first 3 technologies could be deployed right away at some cost, although at minimal cost in the case of the passive daytime radiative cooling. And then it's the mirrors in space, which are the most conceptual and expensive of all the methods, either carbon dioxide removal or solar radiation management.